Welcome to Quantum Computing for Computer Scientists. Happy Valentine's Day. We will learn about this most romantic of all subjects, quantum computing. This is a talk aimed at computer scientists. We will not go over very much, if any, physics during this talk. We won't go over like the double slit experiment or uncertainty principle. We're not learning about any of that. We're going to come up with a computational model, which you will all find it fairly intuitive, I think. Use a state machine. And we will run a quantum algorithm on it, show that it outperforms a classical computation model. And then we'll end with some demos, including a running program in Q#, Microsoft's quantum language. This is the gate quantum computation model. It looks a lot like the classical computation model, where you have like bits and you send them through logic gates and transformations are applied to them. There's another computation model called the quantum annealing model, which is used by D-Wave, if you've heard of that. That's something different from what we'll be going over, but people think they might be equivalent. The jury's still out on that. Anyway, I'm sure you'll have a great time. So, I'm sure all of you have your reasons for being here, but here are 3 reasons I've come up with if you need some additional convincing why you should learn quantum computing. The first is that quantum supremacy is expected this year, this very year. Quantum supremacy means we have a real problem running on a real quantum computer, which in real time runs faster than the same problem on a classical computer. So Google has announced they think they'll do it this year. If they do, it's a really big thing. So it might be in your future. Who knows? 5, 10 years, we could all be running some really tricky problems on quantum computers. So we have lots of large companies, Microsoft, Google, Intel, IBM. They're all investing billions of dollars in quantum computer development. There are lots of really exciting applications. This is the one that everyone's heard about, Shor's algorithm. When this paper came out, it lit the world on fire. People were like, wow, quantum computers could actually have real economic impact. We could factor RSA and undermine our global financial system, which is pretty cool. Here's one that programmers will, I think, appreciate, which is we can search an unordered list in square root n time. So you think for an unordered list, you have to check every element. That's on. You can just get a nice speed up, just square root n queries on a quantum computer, which is pretty nifty, generally useful. And here's the one which I think is probably is the best probability of changing the world. Sorry, programmers, square root n search probably won't change the world too much, which is we might be able to have an exponential speed up in simulating quantum mechanical systems. So things like drug design, if you simulate like biological molecules interacting, things like that, it could like massively speed up a lot of our biological research. And everyone talks about like nitrogen fixation for this. That's like part of the main Microsoft sales pitch. But this is the one that actually motivated me, the bottom one, which I think from talking to a couple of you before the presentation began also motivates you. It's intellectually interesting. And it's interesting because it's just kind of outside my intuition. Like I think all of us at this point in our careers can basically look at any digital or mechanical system and have like a ballpark idea of how it works, right? But if you look at a quantum computer, like how can a quantum computer outperform classical computation? It doesn't make any sense. Like there's no way I could even like start to guess how it would work. And so I really wanted to learn it. And I think there's a reason for this. And this is kind of getting a bit philosophical. But our language, our informal language that we use, developed in a very classical world. It is simply not equipped to deal with the quantum world. And this is why any pop science article you've read on quantum phenomena, it doesn't really ring true. All the metaphors, they don't really make sense. Because we're trying to express it in this language which developed in a classical world. We need to learn a new language, which is the language of mathematics. And that is the only thing which will actually let us understand quantum mechanics, is to learn it mathematically. All metaphors and analogies will lead you astray. There's a famous quote here by a physicist named David Mermin, which is, "Shut up and calculate," with regard to quantum mechanics. So some grad students, maybe they lean back in their chair and they're like, oh, what does this all mean? Shut up and calculate. Just trust the math. The math is the only thing which will not lead you astray. OK, here's how this presentation will break down. First, we're going to learn how to represent computation using super basic linear algebra, matrices, vectors, matrix multiplication. Then we will generalize that to learn about qubits, superposition, and quantum logic gates. And finally, we will use all those tools we've developed to go over the simplest problem where a quantum computer outperforms a classical computer. This is called the Deutsch oracle problem. I mean, there are a bunch of problems, but this is the simplest. And finally, it'd be almost negligent to let you get out of here without learning about quantum entanglement and teleportation, just because with the tools we'll develop, they're like so easy to understand. So we'll have bonus topics, and then we'll have some demos. All right, let's get to it. You'll become very, very familiar with these two vectors. This is how we represent a 0 and a 1, the two values of 1 bit in classical terms. So the top one is just 1 over 0, and the bottom one is just 0 over 1. You can also write them in that weird like angle bracket thing. That's called Dirac vector notation. So you have a 0 in there. That means this is the value of that vector. If you have trouble remembering this, just think of it like an array indexed from 0. And so there's a 1 in the 0th index. That means it's a 0. There's a 1 in the first index. That means it's a 1. OK, everyone's fine with this? You'll be very familiar with this by the end of the presentation. We're going to go over matrix multiplication really quickly. So yeah, we're going to see that. OK. The way to think about matrix multiplication, just to review it for you, most of you will have gone over this in your linear algebra courses like the first or second day. So if we have a matrix multiplied by a vector, you kind of like take this horizontal row and then flip it and multiply it pointwise with these vector values. So a times x, b times y. And that's how you get the top one. Then you do the same thing with the bottom row. C times x, d times y. And you get a 2 vector. The same thing happens with 3 by 3 matrix, a times x, b times y, c times z, and you get this matrix. You can also this vector, you can also multiply matrices together. We won't really be doing much of that. And there's a very special matrix called the identity matrix, which has zeros everywhere except for ones along the main diagonal. And anything multiplied by the identity matrix is itself. It's just like multiplying by 1. In fact, usually you refer to the identity matrix by the symbol 1. Now, thankfully, for simplicity, a lot of the matrices we'll be using look a lot like this. They're mostly zeros with just some ones. And you can notice, is a nice rule of thumb, that relative to the identity matrix, this matrix has the middle 2 rows flipped. OK? And that's actually the action it has on anything it multiplies. So it flips the middle 2 rows. It's a nice sort of rule of thumb to remember how matrix multiplication works. Does anyone have any trouble with this? Because you really need to know this in order to go ahead. Like, you got to know it. OK, great. Operations, actually, I'd like to make this a quiz. Can anyone tell me what are the 4 operations on 1 bit? There's 4 of them.
1 bit.
1 bit.
And or exclusive.
Those are on 2 bits.
Oh.
Not. Identity.
Not.
Identity, not.
Set to 0, set to 1.
Set to 0, set to 1. There we go. Good. Yes. So we have identity. Just f of x equals x. Negation, fx equals not x. Constant 0, it's always set to 0. Constant 1, it's always set to 1. You can see with the diagram how it kind of looks. OK? And we can write these as matrices. So the identity is just the identity matrix. This, remember, is our symbol for 0. Identity multiplied by 0 is 0. Identity multiplied by 1 is 1. Here's negation. You flip it from 0 to 1 and 1 to 0. Same thing for constant 0, constant 1. So I hope I've convinced you we can represent very simple functions, at least, with matrices multiplied by our 0 and 1 vectors. OK? And remember these 4 functions, because I will quiz you later on them. They'll come back up. So let's talk about reversible computing. Reversible computing is a neat sort of buzzword. If you've ever read the popular sci-fi book Accelerando, it talks about reversible computing. And basically, it means that if I tell you the operation I did and the output of that operation, you can always tell the input of that operation if the operation is reversible. So intuitively, operations that just shuffle bits around, like permute them, they are reversible. But operations that like erase bits and then overwrite them are not reversible. And in our previous slide, identity and negation are both reversible. Because if I say the output is 1, and I put it through the negation gate, that means the input was 0. You can always tell that. But if I say the output was 1, and I put it through the constant 1 operation, you can't tell what the input was. It's not reversible. It erases information. And the nice thing about quantum computing, which you can remember, is that quantum computers only use reversible operations. Those are the only ones we care about. So the only operation we actually care about on the slide is really negation. Like also identity, but it's the same as doing nothing. A further fun fact about quantum computers is they actually only use operations which are their own inverses. So not only are they reversible, but if you apply them twice, you'll just get back the same input value. And we're going to go in a little, this is kind of like getting into pop science, but whatever. There's something called the von Neumann-Landauer limit, which is the smallest amount of energy physicists have calculated is necessary for the simplest possible calculation, which a race is non-reversible. And reversible computing might eventually let us go beyond that limit, more efficient than that theoretical limit. Now, currently, processors are use millions of times more energy than the von Neumann-Landauer limit. But 50, 100 years from now, who knows? Pretty nifty. All right. This is something you probably did not go over in linear algebra, but don't worry. It's still pretty simple. It's called the tensor product. So if you have the tensor product of two vectors, it's kind of like you take the second vector and you tile it for each element in the first vector. So x0 gets its own copy and x1 gets its own copy. And then you multiply it out, so you get eventually x0, y0, x0, y1, etc. It might be easier to look at this with real numbers. Here we have 1 times 3, 1 times 4, 2 times 3, and 2 times 4 to get this. Here's how it looks like with 3 vectors. You get this like giant array. Don't worry about it too much. And I'd like to point out that if we use our 0 and 1 values, you end up with a vector which has a 1 in only a single position. OK. Does anyone have any real trouble with this concept? If I gave you 2 vectors, you could probably calculate the tensor product. It's not entirely difficult. All right. But the final point I made leads into how do we represent multiple classical bits? And we represent them by their tensor product. So 0, 0, remember, we tensor, this is our 0 symbol. 0 tensored with 0 is this product state, we call it. 0, 1 is this product state. 1, 0 is this product state, like 0 times 1, 0, 0 times 0, 0, 1 times 1, 1, 1 times 0, 0. OK? And 1, 1 is this product state. And similar to just the single bit, you can think of this as an index in this vector array. So this is 0. There's a 1 at the 0th position. This is 1. There's a value at the first position, counting from 0. And this is 2, value at the second position, 3, value at the third position. OK? This is the only time I will tensor 3 bits together, thankfully, because as you notice, they grow exponentially in size. But it works for this. So 4 is 1, 0, 0. You have 0, 1, 2, 3, 4 is where the 1 bit is. OK. Yeah, so we call this the product state. We can always factor it out into its individual states. And the product state of n bits is a vector of size 2 to the n. Here we see a sort of whisper of the power of quantum computing, this exponential term. But hold that thought. We'll get back to it. So we're going to learn a very important operation, very fundamental to reversible computing and quantum computing. It's called C0, or conditional not. It operates on a pair of bits. You designate one bit the control bit. The other bit is the target bit. So the control bit, if it's 1, it flips the target bit. If it's 0, it leaves the target bit alone. And the control bit is always left alone. So if we have the most significant bit of a 2-bit system is control, the least significant bit is target, then 0, 0, since this is the most significant bit, it's the target bit, it just goes to 0, 0. 0, 1 goes to 0, 1. Now 1, 0, since the control bit is 1, maps to 1, 1, right? Because it flips the other bit. And 1, 1, since it again flips the target bit, goes to 1, 0. OK? And this matrix, you can actually kind of write it. You see there's like a sort of correspondence here. We flip the bottom 2 rows versus the identity matrix. And this, I claim, which I will show in the next couple slides, will change our product states according to the semantics of C0. So does everyone get the semantics here? We have a control bit and a target bit. Control bit's 1. We flip the other bit. Pretty good? OK. Now, this is a lot of math. But don't panic. We're going to go over it step by step. If we apply the C0 gate to 1, 0, remember that this is the control bit's 1, so we're going to flip the other bit. So we expect it to go to 1, 1. Now let's expand this out step by step. So 1, 0 corresponds to this tensor product. This is the matrix from the previous slide, and we're applying it to our product state. Remember, it's just going to flip the bottom 2 rows. So we get to this product state, which when we factor it out, indeed gets us 1, 1. OK? Now let's do it with 1, 1. Same thing. We have our familiar matrix multiplied by this product state. We go to here, which we factor into 1, 0. So I hope I've convinced you at this point that we can use matrices to represent kind of more interesting logical operations than just a bit flip. Does anyone have any trouble? Yes?
So is that factoring always possible or practical for larger vectors?
It is practical, yes. Not always possible, which kind of, we'll get into that when we get into quantum entanglement, basically. But good question. Okay. So this is fine for everyone. Nobody's lost in the gigantic equations here. Okay, we're going to go over 1, 0 then. Or sorry, 0, 0. So the control bit's 0. That means we're going to leave the other bit alone, right? And we see that indeed this is what we do, and same with for 0, 1. Okay, so everyone, well, maybe you're familiar with how classical computers or like real CPUs, they're all built on the sort of NAND gate. Like everything is fundamentally built on NAND. And the C0 is kind of the analogous NAND for reversible computing. It's like a really basic thing that is used to build up larger, more complicated logical statements. Like, so I'm sure if I gave you a task, like build some more complicated logical formula with C0, you'd probably be able to do it at this point. You just like stick them all together and eventually it comes out. I will note that it's not actually universal. You can't make every logical function with a C0 gate. You need something called a Toffoli gate. But we won't see that in this presentation. And we've learned everything we need to know about how to use linear algebra, to represent classical computation. And we can now go on to quantum computing. So to recap, we learned that we can represent classical bits in vector form is 1, 0 for 0 and 0, 1 for 1. We can represent operations on bits by multiplications on their bit vectors. We learned that quantum computers only use reversible operations. And in fact, the operations are their own inverses. And multi-bit states, we write, is the tensor product of our single-bit states. Finally, we learned about C0, which is a very fundamental gate in reversible computing and quantum computing. So this is everyone's following along so far? This is pretty simple, right? It's not that bad. Okay, let's make the jump. Qubits. And I will surprise you, we have been using qubits all along, actually. The C bits are just special cases of qubits. And we represent a qubit in general by a vector of two elements, A, B, where A and B are complex numbers. Don't worry, we'll only use real numbers for this presentation. We're keeping it simple, only using real numbers. And we have the constraint that A squared plus B squared is 1. So 1, 0, and 0, 1 fit this definition, because 1 squared plus 0 squared is 1, and 0 squared plus 1 squared is 1, right? Now, here are some example qubit values. This is one with which you'll become very familiar. It is 1 over root 2, 1 over root 2. Can anyone tell me what 1 over root 2 squared is?
1/2.
1/2, exactly. 1/2 plus 1/2 is 1. So this is a qubit. What about 1/2 and root 3 over 2? What's 1/2 squared? It's 1/4. So 1/4 plus 3/4 is 1. Here's an interesting thing. We can actually use negative numbers now, because a negative number squared is a positive number. So negative 1 squared is 1. 1 plus 0 is 1. And the same thing here. It's just the same as this first matrix, but one of the values is negative. Pretty neat. Not bad so far, right? OK, but you might say, this is kind of like saying that a qubit has a value which is not 0, 1, but actually both 0 and 1 at the same time. This is called superposition. Everyone's probably heard of the Schrodinger's cat being both alive and dead. That's just like a pop science-y way of articulating this concept, sort of. And the interesting thing about a qubit being in superposition, it means we can kind of, I want to really qualify this, kind of compute with the values of both 0 and 1 at the same time, which again is the sort of whisper of some quantum speed-up power. Okay. Now, how this works is when we measure this qubit, it collapses to our familiar values of 0 and 1 with some probability. And this is what we usually do at the end of a quantum computation to get the final result. We send it through the measurement gate. We see what the result is. So how the probability works is if you have a value AB, it collapses to 0 with probability A squared and 1 with probability B squared. So if we look at our familiar qubit from the previous slide, 1 over root 2, 1 over root 2, it has a 1/2 chance of collapsing to 0 and a 1/2 chance of collapsing to 1. It's like a coin flip. Now, if we just measure our classical qubit or classical C bits, the 1, 0 has a 100% chance of collapsing to 0, and 0, 1 has a 100% chance of collapsing to 1. So it's sort of idempotent in that way. And I found it useful here to give people a sort of physical intuition about what we're doing, what a C-bit is, or a qubit is. If you've heard of polarization, you've probably bought like fancy sunglasses. It says that they're polarized. So polarization is actually a sort of quantum phenomenon. You can be polarized like this way or this way, and your glasses will only be polarized a certain way, so they'll only let light polarized in this way through, basically. It turns out that qubits, you can think of like this, a photon being polarized this way is a 0, and a photon being polarized this way is a 1. Superposition means it's actually like both, right? So it could actually go through both gratings. And then if you measure it, and a way to measure it is just to like fire it through a grating and like see whether it goes through, then you can collapse it to 0 or 1. So that's our sort of intuition, pinning this to a physical concept. Of course, we found that photons actually make very, very poor qubits. They tend to collapse too easily, so we don't use those, but you can maybe think of that. Does anyone have any confusion here, really, about how this measurement process, collapse probability works? OK, great. We will learn about multiple qubits. The same is multiple C-bits. We represent them by the tensor product. It actually, why is it doing that? OK. Hold on. Laser pointer. OK, there we go. Nope, that's not. OK. So if we have 2 qubits and we multiply them, the sum of squares identity actually it is maintained. And so if we consider our perfectly balanced 50% coin flip qubit, and we tensor it with another coin flip qubit, we get this 4 vector with 1/2 in every single column. And 1/2 squared is, of course, 1/4. So 1/4 plus 1/4 plus 1/4 plus 1/4 is 1. This maintains the property. And the way to read this is when you measure these 2 qubits, it has a 1/4 chance of collapsing to 0, 0, 0, 1, 1, 0, and 1, 1. This is sort of the probability of when you measure it finding a 1 there and 0 everywhere else. So we could find that it's a 1/4 probability of finding a 1 in this position and all 0s everywhere else. Does that kind of make sense for multiple qubits? OK, great. You guys are just trucking along, no problem. It's to be super easy. Yes?
So I have a question.
Absolutely.
So there's only going to be one 1 left in the vector?
Yes.
There couldn't be 2 1s.
There could not be 2 1s, because that would actually violate our a squared plus b squared equals 1 constraint.
Okay.
But yeah, after measurement, there will only be one 1 here in this 4 vector, which we can then factor into 2 bits, actually. OK. Yes?
Right. Did we also define collapsing for that longer vector?
Yeah. So if you measure these 2 qubits at once, you can think of this product state vector as collapsing. And then that's just the probability of finding a 1 here and a 0 everywhere else. It'll become useful in the future when we can't actually factor out the product state. But that's, anyway. OK. How about operations on qubits? We have these qubits. How do we actually manipulate them? The same way we do with the classical bits. And all the matrix operators we've learned also work with qubits. So for example, negation. If we have our qubit that has a 25% chance of collapsing to 0, 75% chance of collapsing to 1, if we run it through the bit flip operator, now it has a 75% chance of collapsing to 0 and a 25% chance of collapsing to 1. So we can manipulate these probabilities. They're actually called amplitudes with gates. And you can think of like a gates, they correspond to some device scientists have created, which sort of like manipulate the qubits with a gentle touch. Not enough to like collapse them, but enough to like change their state. So pretty neat. And there are also a couple important matrix operators, which we haven't learned yet because they only really make sense in a quantum context. OK, sorry. OK, all right, we're good. The most important one is the Hadamard gate. And what it does is it takes a 0 or 1 qubit, and it takes it to the coin flip state, where it's in exactly equal superposition. The matrix looks like this. It has 1 over root 2 in every single entry, except for a negative in the bottom right corner. So if we multiply that by this, you get 1 over root 2, 1 over root 2. If we multiply this by 1, we get 1 over 2, negative 1 over root 2. Pretty neat. So this is how we actually get into superposition. We use the Hadamard device, which scientists have developed and we can make much use of. So kind of quiz time. Can anyone tell me why we need a -1 in the bottom right corner? Why do we need a negative sign here?
It's like a matrix, almost like a provision
It's like a,
catches it. And I don't know exactly why, but it seems like it's.
well, the answer basically is it has to be reversible. So if we didn't have this negative number here, then both 0 and 1 would map to the same value, and it would not be reversible. So we need this negative sign. Yes, correct. Okay,
Wait, question?
yes.
Review of superposition, what does that mean exactly in this?
Superposition, yeah. So superposition means that a qubit is kind of in both states 0 and 1 at the same time.
Okay.
And I want to be, I guess, really clear about something here. This doesn't mean the qubit is secretly 0 or secretly 1 and we don't know. It means it's actually in both at the same time. This is like just quantum weirdness. This is just like what happens at the very, very small level of our world, which is that things don't have definite values until we measure them.
But here you have 0 when in superposition is 1 over root 2, 1 over root 2. And 1 in superposition is 1 over root 2 minus 1. So
Yes.
they seem to have different values, but they're representing conceptually the same thing.
Right. Which is, so this kind of comes down to the distinction between the quantum and classical world, which is that from the classical perspective, these two qubits are kind of the same. They both have 50% probability of collapsing to 0 or 1. But if we stay within the quantum realm, this sign information is preserved as long as we don't measure it, and it can affect our computations.
So kind of like, it's got a 50-50 chance, but it has a sense that it used to be a 1.
Has a sense that it used to be a 1. Not really. It's just it ends up in this state, which is different within the quantum realm than this state. These are two different states.
Okay.
Yes.
Both with a 50-50 chance.
Yes, exactly. Both when you measure it and convert it into the classical world, come down with a 50-50 chance. Yes,
Okay.
but they are different, and they have different computational properties. Okay, now I'm going to show you something really cool about the Hadamard gate, which it actually takes us out of superposition into the classical bits. This should be unsurprising. Everything's its own inverse, right? If we just apply the Hadamard gate to our value here, our coin flip value, we get 0. And for this one, we get 1. So this suggests to us a sort of quantum computation structure. We can start with our classical bit values. We put them into superposition, do a bunch of quantum stuff to them, and at the end, if we're clever, we can transition them to 0 or 1 so that our whole computation was deterministic. Pretty neat, right? Okay. Now, I should say that not all algorithms work this way. There are algorithms like Shor's algorithm, which only gives the right answer 50% of the time. You can't be clever and always get the right answer. It's just not doable. But the problem we'll look at does give this sort of deterministic property. So does anyone have trouble with this concept? We can transition out of superposition without measurement. Pretty interesting.
Can you go over this transition from a classical kind of computation to quantum and then converting it back?
Yes.
Classical, like let's say 2 plus 2, how would that look like in?
How would
I mean, just the simplest type of math that we do.
the simplest type of math? Well, we're going to go over that basically. We're going to go over a problem. There are certain problems where quantum computers are better than classical. Like the addition is not one of them. It works the exact same way in both. It should also be said that all classical computation can be done on a quantum computer. All you do is just restrict all the values to 0 and 1, and it works. But it's kind of a waste because you can also use all the extra values that we found. Okay. And we've actually sort of defined a state machine here, which I'm sure many of you will appreciate if you're software engineers or computer scientists. Here is the action. OK, so this is the unit circle, which many of you will remember from high school trigonometry, right? It's a circle of radius 1 around the origin. Here's the x axis. This is the y axis. You can think of the top value is the coordinate on the value of the x value, and the bottom one is the y value. So our 0 value is at position 1, 0, which is along the x-axis. our one values at position 0, 1, which is along the y-axis. And this is the bit flip operator. It defines transitions around this unit circle. So 0 goes to 1, 1 goes to 0. 0, negative 1 goes to negative 1, 0, which when you collapse them, this is 0, this is 1, and vice versa. Excuse me. And if we look at the superposition values, here's something interesting. The bit flip operator really kind of has no effect on them. You know, for this one, if you flip it upside down, it's just it stays itself. Same with this over here. This one's kind of interesting in that it transitions you all the way across the unit circle, and we'll make use of that. But yeah, OK. This is pretty much the full action of the bit flip operator on the unit circle. I should mention here that if we were using complex numbers, this would actually be a sphere. Much more difficult to sort of intuitively represent or graphically represent. So we're sticking with real numbers. They suit us just fine. But it's nice to know that additional dimension is always available to us if we want to make our computation even more powerful. And then here's the action of the Hadamard gate, which we saw the past couple slides. It takes us from 0 to 1 over root 2, 1 over root 2. 1 to 1 over 2, negative 1 over 2. And kind of symmetrically, it also works in this way over here. So we have a nice state machine that we've developed. And now we can start running things on the state machine. Very nice intuitive sort of representation. You don't need to do matrix multiplication all the time. Everyone kind of gets this? OK, great. So here's an example of something we could run through the state machine. Here I'm introducing something called quantum circuit notation. You can think of the qubit traveling along this line, has these operations applied to it as it goes through the boxes. So x is bit flip, h is Hadamard, and then so we go bit flip, Hadamard, bit flip, Hadamard, bit flip. And if we start out here, we go bit flip, Hadamard, bit flip, Hadamard, bit flip. So we start out at 1, 0 and get to 0, 1. We get across the circle. And note this is reversible, so we can also go this way and get back. So this is kind of how we'll be we'll be doing all of our computations like this, basically, just hopping around the unit circle. It's pretty simple, pretty intuitive, right? It's just a state machine. We use this in classical computing all the time. It just has a bit of weird rules with collapse and whatever, but don't worry. OK. Now we have everything we need to learn the simplest problem where a quantum computer outperforms a classical computer. We learned that c-bits are just a special case of qubits. And qubits are two vectors of complex numbers such that a squared plus b squared equals 1. We learned that qubits can be in superposition. They are probabilistically collapsed to c-bits by measurement. Multi-qubit systems, we learned, are tensor products of single qubit systems, same as with c-bits. Matrices, again, represent operations on qubits. And we learned about the Hadamard gate, very important, which takes our 0 and 1 bits to superposition and back. And finally, we learned that we can think of qubits and their operations as forming a state machine on the unit circle or unit sphere if we're using complex numbers. It's actually called the Bloch sphere, B-L-O-C-H sphere, if you want to look that up for the full complex numbers, but unit circle, just fine for us. OK. So we're going to learn about something called the Deutsch oracle. This is originally proposed by David Deutsch in, was it like 83 or something like that? And the problem is this. Imagine I show up at your doorstep, and I give you a package. The package is just this black box. It's just a horrible present. It's a black box which has a function on 1 bit. So it's one of those 4 functions on 1 bit. Do you remember what those are? I said I would ask you about them.
Set 0, set 1.
Set 0, set 1, identity negation. Exactly. So one of those 4 functions, I don't tell you which one, is inside this black box. It has a wire going in and a wire going out. So you can send in values, see what goes out, but you can't actually look inside the black box. OK? So how many queries on a classical computer would it take to figure out which function is inside the black box? 2, exactly. You send in 0, see what comes out. You send in 1, see what comes out. That'll uniquely identify which function it is. Now, how many queries do you think it takes on a quantum computer? You're wrong. It's 2. And I say this to illustrate an important point, which is quantum computers, they don't really compute with all values simultaneously. At the end of the day, you collapse your qubit to a single bit of information. And a single bit of information is not enough to uniquely identify 4 functions, one of 4 functions, right? You need 2 bits at least. So this actually takes 2 queries on a quantum computer. Well, not too exciting so far. Now, what if instead of wanting to know which function it is, we just want to know whether the function is constant or variable? So the constant functions are the constant 0, constant 1. They always map to 0, always map to 1. The variable functions are identity and negation. So how many queries would this take on a classical computer? 2. You put in 0. If you get 0, you don't know whether it's identity or constant 0. If you get 1, you don't know whether it's bit flip or constant 1, symmetrically with 1. So it always takes 2 queries on a classical computer, even though there are 2 categories. So really, we only need a single bit of information to tell us which category it's in. But how many queries do you think it takes on a quantum computer? I kind of burned you last time, so maybe you're a bit shy.
I'm going for 1.
1, you are correct. We can do this in a single query on a quantum computer. We can tell whether it's constant or variable. This like undeniably outperforms a classical computer, and we're going to learn how. Okay, we do it with the magic of superposition. But first, we have to define what each of those 4 functions look like on a quantum computer. We have an instant, obvious problem with the constant functions. Can anyone tell me what it is?
Not reversible.
They're not reversible. How are we going to write these non-reversible functions on a reversible computer? This is actually a really common problem in quantum computation. You really often have to deal with non-reversible functions. You have to write them in a reversible way. And the hack we do is this. So originally we had this, right? We had an input and an output, a single wire going through. And we just imagined that you put in the value and you get the function applied to that value, right? But the hack that you always do on quantum computers is you add an additional output qubit. So you actually have 2 qubits. We have to rewire our black box. So you have your input qubit, which is unchanged, and then the value of the function on this input qubit is written to the output qubit. Does everyone kind of get this? This is I think, the thing that people have the most trouble with, this necessity. The reason we have to do this is so we can write non-reversible functions in a reversible way. And the way to do that is to have a separate input and output qubit. So when you see larger quantum computations, instead of having all the bits go in and have transformations applied to them and then being measured, you usually have a separate set of output bits. So the input bits go in, they have their value sort of written to the output bits, and you measure the output bits. This is a very standard way of doing quantum computation. So does anyone have any trouble with this? This is a very difficult concept, so yes.
I didn't get it.
Yeah.
Okay. Okay. So do you understand this model, basically? This is what we have now, okay? We need to rewire it. So there are 2 wires going through the box now, okay? And one of those wires we call the input wire. One of those wires we call the output wire. We assume the output wire is just initialized to 0, right? It's always 0. Now our input wire is what we actually give our input in. Like it'd be like 0 or 1 or whatever value we want to give as input to the function. So it goes through the box. It's just unchanged. You know, we don't touch the value of the input wire. But with a function, we calculate the function in here on this input, and then we write its value to the output wire. Okay?
The black box?
Yes, we are rewiring the black box. We have to rewire the black box in order for the black box to really work. So the black box I gave you has to be rewired. Yes?
Did you use the first input, which is the output of 0?
Did I use the first input?
Yeah, because one of them was kind of identity, right? You put the x out, and then it was the f of x.
One of them was X out, and the other was...
So why did we need the other input? So I
Well,
get
so
it
you
that
need the
you
other-
need the x out.
Right. So say we only had this, right? This is the old way of doing it. We can't have a non-reversible function in here, right? For it to be on a quantum computer.
No, that I
Okay,
get.
okay.
Right.
Yes.
But what I'm saying is that on the right side, you
Yes.
have 2 going in, 2 going out.
Yes,
right?
2 going in, 2 going out, yes.
I get why 2 going out.
Yes.
But I don't get why the output of 0 is also going in. It doesn't seem that you're actually using it to produce any of the outputs.
Yeah, you're correct. It's just we need
Symmetry of some sort?
not really symmetry. It's just like how we would write the quantum circuit. We would need 2 qubits in general. So, and we just you're correct that this output value isn't really used.
Is it like a don't care kind of?
No, we do want it to be 0. Because the way that we write the circuit assumes that this value coming in is always 0. Yes?
Why is that ingoing output wire called output?
What? Yeah. So this is kind of weird that like the output of the input is called input. But we basically only really look at this value here is the basic idea. This is like the real output. The input will always be unchanged.
Question. So
Yes.
if I had two black boxes in series, in
Yes.
effect, the upper input, which you have labeled as output
This
there,
one, yeah, that's a bit weird.
and the second stage would be the f of x output of the first stage?
Yes. Well, okay. So you're saying if you had these in series rather than sort of in parallel, what we're doing? Or is that what you're saying?
Yeah, I want to do two operations, one and then another one. And the black box is doing some operation.
The black box is doing some operation. You can have as many operations as you want in here, inside this black box, basically.
True, but I'm trying to conceptually understand whether I would take the f of x output upper right, and that would be the
Input to
input,
yeah.
the next one.
Absolutely. And in fact, I said that this black box assumes this value is 0. This is maybe throwing a bit much at you. But actually, we can break that assumption and send it some other value, which maybe will get us more information, which is in fact what we'll be doing. So the black box, the working of the black box assumes that the output input is 0. But we can break that assumption and be tricky.
My way of thinking was I didn't have any other value for the first stage, but for subsequent
Yes.
inputs, I do have one, so I could use it if I wanted.
Yeah, you could. Yeah, and you might get some interesting values, which you actually will. Okay, I swear, this is the most difficult part conceptually of this entire presentation. So if anyone has any trouble with it, please just let me know. Ask any questions. We can spend as long time on this as we want. Yes.
As we go ahead, is there some additional clarifications to this? Because I didn't get it.
Okay, well, we'll go over how we'll write each of the 4 functions in this way. So maybe that will help. So, for example, constant 0. Here's how it would look. X goes in, X goes out. It's unchanged. Now, the output is always going to be 0, right? That's just what the constant 0 does. So we always want this value in the upper right to be 0. If we assume 0 goes in, this is our circuit diagram. Neither of the 2 wires make any modifications, right? It's a straight wire. Does that sort of make sense? Okay, we'll see. The next slide. What about for constant 1? We want 1 to go out here, right? This is our function output value. And if we assume 0 is the input here, all we do is we do a bit flip right here. And that gets us this the semantics we want. Is anyone having any trouble with this so far? I swear, this is the most difficult part. So if you get this, you're golden. Yes?
So instead of these labels output and input, could you call them something like computation and spare?
Sure. Yeah, you could. You could call it like the compute and the spare bit. Yeah, that also works. It might reduce some confusion about there being an output and input.
So again, why is it called output?
Why is it called output? Because we call this the output qubit because it's just the place that we write the output of the function. But we could call it like compute and spare or something like that, like he suggested. Like this would be the spare sort of bit that we write the function output to. Yes.
So we did this to have a reversible computation, right? Why is this
Reversible?
Can you compare the reversibility of these two? Like, why is the right one reversible one?
Absolutely. Okay. So let's consider this one right here, right? We have our black box with a single wire. And say we want to do the bit flip operator. So that would just be, sorry, not the bit flip operator. The bit flip operator is reversible. Say we want to do the constant 0 operator. We always want to map this to 0. So you need some operation right here that would map this to 0. But it'll be the matrix 1, 1, 0, 0. But this is not a valid operator in a quantum computer because it's not reversible. So does that kind of make sense? It's just we can't construct a device which does this. It's just not permitted by physical reality. All this math and stuff I'm showing you, it's not like special. It's just we found that it corresponds to the semantics and workings of a quantum system. And so it's a nice way to reason about it, basically. Okay. Versus, yeah. Of course, if we want to write constant 0 here with the 2 input, or the 2-wire model, it would just be blank, right? Or if we want to do This is constant 1, always maps to 1. We saw that this has an x gate here. And this is reversible, right? Okay, so we managed to write a non-reversible function in a reversible way. If you got this, congratulations. This is the trickiest part. It took me a while to figure out why we needed to do this, staring at the textbook. Does anyone have any confusion here? Okay, so remember constant 0 is just blank. Constant 1 has a single x gate. Yes?
So is the point that you always end up with a 4x4 reversible matrix by doing this in the black box?
Yes.
Okay.
Yeah, the black box is always a 4x4 reversible matrix applied to a product state. You're correct. Although we will be not going into the math in that way, we'll just be using the state machine to look at it. But the math is very easy for you to do yourself. Okay, so let's look at identity. This is a bit more complicated. This is the C0 gate, okay? Where this is the control and this is the target. So we'll end up with, so input again is unchanged. We want output, we assume it's 0. We want to end up with the value x, right? So if 0 is sent in here, then this is the control bit. So the target bit is just left unchanged, right? So 0 comes out. If 1 is here, 1 is sent in, then the control bit's 1. So we flip this bit, and we end up with 1. Does this make sense? This is kind of tricky. This is a step up in complexity of our circuit. But everyone's fine with this? Wow, OK. Can anyone guess how we'll do negation?
You could hard set the control bit to 1.
How can we hard set the control bit to 1?
2 controlled knots.
Not 2 controlled knots. It is, we just have an x gate there. So up to here, it's equivalent to identity, right? And then we just flip the output bit, and then we get not x. So those are the 4 circuit values. OK. Everyone's good so far? Everyone knows how we write our 4 functions? Are you ready to see how we solve it on a quantum computer? We use this. So we're going to break the assumption that this value goes into the black box as 0. We initialize both input and output qubits to 0. We bit flip them, so now they're both 1. We put them through the Hadamard gate to put them into equal superposition. Then we send them into the black box. One of those 4 circuits is applied. Then we do the post-processing. We send them through the Hadamard gate again, and we measure them. This is measurement. And I claim, and I will show to you, that if the black box function is constant, the system will be in state 1, 1 after measurement. Like this will have value 1, this will have value 1. We're using input as the most significant bit, by the way. And if the black box function is variable, then the system will be in state 0, 1 after measurement. So this will be 0, this will be 1. And we will know whether the function is constant or variable in a single query. Pretty nifty, right? I'm going to show you how it's done. First, the pre-processing. Remember, we start with 0, then we bit flip both, and then Hadamard gate both. So we start here. Bit flip takes us up to here. Hadamard gate down here. So this is the value that is sent into the black box. Just remember, it's in the bottom right on the unit circle. This is the value right before we send it through one of those 4 circuits. OK? Now let's look at how we do constant 0. So constant 0, remember, it's just blank on both. And the post-processing is a single Hadamard gate. So since no gates are applied, they stay in this bottom right value. And since the Hadamard gate is applied as part of the post-processing, we flip back up here. When we measure this, this is 1, 1. Remember I said the value would be 1, 1 if it were a constant function. So we're 1 for 1. OK? Seem OK so far? All right. Let's add a bit flip, because we're going to go over constant 1 now. So this is the other constant function. Now remember, if we do a bit flip in this state, we flip across the unit circle over here. And the Hadamard gate then takes us down to here, 0 and -1. When we measure it, we again get 1, 1. OK, so we're 2 for 2. Not bad, right? OK, things get a bit more complicated. Does anyone have any trouble with this so far? Any of these yes? Do you
I just didn't get like why result is 1, 1.
why it works out to 1, 1?
Yes.
Well, that's a good question. Okay, so we're up here, right? If we measure this, then what value do we get? This is just 1. Remember, this is the value of the 1 bit. So if we measure 1, we get 1. Yes. Now down here, if we measure this, we also get 1 because negative 1 squared is 1. So it's a 100% chance, 100% probability of collapsing to 1. And so we can say this is 1, 1. This is like the most significant bit, and this is the least significant bit. So we end up with 1, 1. Does that answer your question?
Yeah.
Okay. Great. All right, let's get on to something more complicated, which is C0. This is going to get a bit weird. But this is how we do identity, remember. The input bit is the control bit. The output bit is the target bit. And don't panic. I'm going to show you why this is on the next slide. But the action of C0 is to take our input qubit up to here. It's the green line. This is weird for 2 reasons. One is that the C0 is supposed to leave the control bit unchanged, right? But here, this is the only thing the control bit is the only thing that's changed. And this sort of action is a bit odd. But don't worry, I'm going to show you the math, the reason why this works on the next slide. But just for now, so we flip from here up to here. And then when we do the Hadamard gate to post-process, we end up in state 0. So 0, 1. Pretty neat. OK, here's how the math works. We're applying the C0 gate to the state 1 over root 2, negative 1 over root 2, and 1 over root 2, negative 1 over root 2, right? When we tensor these together, we get this ridiculous matrix, which I'm going to factor out 1/2 just to make it readable. So we have the matrix 1, or vector is 1, negative 1, negative 1, 1, right? Now, we remember this familiar matrix from the C0 slide. When we apply this matrix to this vector, we get this, right? We flip the bottom 2 rows. Now, when we factor this, remember this is the product state, and we can factor it into the individual state, we get this tensor product. If you ignore everything in the middle and just compare our start values to our end values, this is the output, or least significant bit. This is unchanged, right? This is still 1 over 2, negative 1 over 2. The input bit, which we started out as 1 over 2, negative 1 over 2, ends up as 1 over 2, 1 over root 2. This is just the action of the gate. So this is kind of a limitation of our visualizer that we can't really show the state transition. But I hope I've convinced you that this arrow is in fact what happens. Does anyone have any questions about this? OK, so we're 3 for 3, right? I said the output value would be, or the measured value would be 0, 1 if it were a variable function. And indeed, it is, as I said. So for 3 for 3. Let's go over the very last one, which is negation. It's a C0 and then a bit flip, right? Let's see how that works. Again, we have this arrow taking us up to here. And the bit flip takes us across the unit circle. And we do the Hadamard post-processing to get us down to here. When we measure these, we get 0, 1. 4 for 4. Huh? Single query. Outperformed classical computation. Pretty nuts, right? Pretty nuts. OK, so we did it. We have outperformed classical computing. Classical computing is in the dust. It's done. It's dead. So you might think, like, yeah, I see how the math works, but what's the intuition? I'm going to tell you the intuition. The intuition is the difference between within the categories was a single negation gate, right? So if we go back to here, so we have constant 0 and constant 1. The only difference between them is a single negation gate. When you apply a negation gate in a superposed state, it doesn't really have any effect, right? So we kind of neutralize the effect of the negation gate. So we neutralize the difference within the categories, and then we magnify the difference between the categories, which is that the variable functions have a C0, and the constant functions do not. So we magnify the effect of the C0 and minimize the effect of the negation. And that's the neat thing about, that's a powerful thing about quantum computing, which is that you can change the action of various logic gates by putting yourself in superposition in different sort of states and stuff. So that's pretty neat. And this problem, you may say, like, OK, well, yeah, great, whatever. It's really contrived. When do I ever do this in real life? That's a good question. And it was contrived back when it was announced, I think it was 1993. But then a generalized version of this function was found, which it takes n bits as input, not a single bit. And the n bits either all map to the same value, that's 2 to the n possible values. They all map to the same value, or they equally map to 0 or 1. They're constant or balanced, it's called. So it's a kind of just a generalized version of this. It turns out we can still solve that on a single query. Exponential speedup. Huh? Exponential speedup. A single query versus on a classical computer, you have to try all 2 to the n values, right? Before you know whether it's constant or variable. Pretty nuts, okay? And then there's a variant of that problem, everyone's kind of like building on top of each other. It's called Simon's periodicity problem. It's again, you have like a black box and you try and figure out some properties of the function. And then once that came around, Shor, he looked at this and he's like, oh, we can use this to factor large integers. And so he came up with Shor's algorithm. And that's when like the whole field really caught fire. So I hope I've convinced you that while this individual problem is kind of contrived and not that useful, it's the base, like the foundation of some very interesting computational properties. Does that make sense? Anyone have any questions? You're all like convinced that we just crushed a classical computer right here? Yes?
On the Microsoft site, there's an article where the gal's saying that with quantum computers, you can take programs that take billions of years to run and run them in a week. Is this
could be that. I mean, yeah.
You
You have an exponential speed up.
hardware?
If you have like, I don't know, what would take something like 1 billion years to run? Like if you have an 80-bit function, like 2 to the power of 80 versus like a single query, that's probably 1 billion years versus a week, something like that. So.
Actually, a question. So
Yes.
I understand the speed up, but this is the speed up in answering the question from the output coming to get the input, right? Whether the function was a constant function or
Yes.
right? But in what context is that question an important?
Great question. Why do we care about this sort of thing? So for example, in Shor's algorithm, you can construct a question like, does this integer have a certain factoring structure, basically? And you can tell a property, like whether it has that property or not, basically, which will allow you to, and if it does have that property, you can like factor it, pretty much. It's very, very hand-wavily explaining how Shor's algorithm works. So you can construct a lot of problems in terms of, does this function have a certain property or not, which you can find efficiently on a quantum computer. I hope, yes.
You mean decision problems?
Mainly decision problems. Although, like as we know from theoretical computer science, decision problems can usually be turned into like general find me the answer problems and vice versa. So, yeah. Okay, pretty good so far. And yep, to recap the whole presentation, we learned how to model classical computation with basic linear algebra. We learned about qubit superposition and the Hadamard gate. And finally, we learned about the Deutsch oracle problem where quantum outperforms classical. Pretty nifty, huh? Okay. Now the bonus topics. With all the tools we have, these will be a breeze for you. You'll never have to read some pop science article about quantum entanglement and like try and muddle through their horrible metaphors. You'll actually know the math, all right? You'll know the math. That is incredible. And we'll go over quantum teleportation, which is super, super nifty. Like it is mind-blowing. Okay, quantum entanglement. You asked a great question, a very prescient question earlier, which is, can we always factor the product state into the qubit state? When we cannot do that, that means that the qubits are entangled. For example, this state. If we have qubits in this state, which is 1 over root 2, 0, 0, 1 over root 2, if we try and factor this, we can't. So let's try and factor this. We should, if we can factor it, we should be able to write it as the tensor product of two matrices, right? Where a times c is 1 over root 2, a times d is 0, b times c is 0, and b times d is 1 over root 2. So we have this set of equations, right? Now, a times d equals 0. That means a or d has to equal 0. If a equals 0, then ac would equal 0, and it doesn't, so a cannot equal 0. If d equals 0, then bd would equal 0, but it doesn't, so d cannot equal 0. So the only solution is there is no solution. We cannot factor this. This is an unfactorable state. And what this means is we cannot separate these qubits. They have no individual value. Their value only makes sense together. They're called entangled. And the way we might think of this is that if we measure this state, it has a 50% chance of collapsing to 0, 0, and a 50% chance of collapsing to 1, 1. So the qubits are coordinating, right? Does anyone have any confusion with this sort of mathematical representation? Okay, let's talk about what it means. Well, let's not talk about what it means yet. We might be like, well, Andrew, I can sling any old value into the vector. How do you actually entangle qubits? It's really simple. If we have 2 qubits, we just put 1 qubit through the Hadamard gate to put it in superposition, and then that qubit is the control bit in a CNOT. 2 gates, that's all we need. Here's how it works mathematically. We start out with 0, 0. We put the most significant bit in superposition, right? And then here's our familiar matrix, CNOT matrix. If we apply it to the product state, we get this. This is the state from the previous slide, right? So really simple to entangle qubits. Okay, what does this mean? I mean, they seem to be coordinating or like communicating or something in some way, right? These 2 qubits. And if you measure 1 qubit, it collapses the other in a coordinated state. Now, the weird thing, here's how we're getting into really weird stuff here, okay? This happens across huge distances. China just this year managed to do this between Earth and a satellite in space. They entangled qubits, put 1/2 on the satellite. It was launched into space. When they measure them, they're the same value. It happens across huge distances. It happens faster than light. It is instantaneous. A 2013 experiment entangled qubits, moved them very far apart, synchronizing with an atomic clock. They measured them very close together. So close together in time that it would have taken light 10,000 times longer to travel between them. So they aren't communicating with any sort of radiation, anything like that, okay? It's instantaneous. It's faster than light. And you might be like, well, it's pretty obvious what's going on here. When the qubits were entangled, they just decided ahead of time what they're going to do, right? Like, that explains everything. But that's called hidden variable theory. This is hidden variable theory. It's the same reason that when a qubit's in superposition, it isn't secretly 0 or secretly 1. It's both. It's the same thing. And hidden variable theory, we're not going to go over the proof why it doesn't work, but basically there's this guy named John Bell, and he showed that if hidden variable theory were true, it had some really weird implications, and therefore it's untenable. It's just the state, it's just how the universe works. They coordinate faster than light. They just do. That's nuts. And you might be like, well, I've been taught my entire life there's a universal speed limit, the speed of light, right? Like, what's up with that? We can't just chuck it all out. And this was, in fact, a big source of consternation to Einstein, the idea that locality wasn't true. And then it was discovered that there's a really important qualifier. You can have faster than light coordination, but you cannot have faster than light communication. So information cannot be communicated. So think about it. If I entangle 2 qubits, I give you 1. We go to opposite ends of the universe. If I collapse mine, all I know is that you collapse yours. When you collapse yours, you will see the same thing. There's no information that can be communicated there, really. So faster than light coordination is OK. Faster than light communication, not OK. OK. Yes?
So coordination does not involve communication?
It does in a way. But communication here is a technical term, which means like I have a bit of information that I can transfer to you, pretty much. So I use the term coordination to try and give a name to something which is not that, but still involves like some kind of coordination, I guess. Like I said, this is a limitation of our language. All we can do is look at the math and see what it does. And our language is not, it was not developed for this. Anything I try and tell you is fundamentally a lie, except for the math.
I have a question.
Yes.
So let's say I have 2 entangled qubits here,
Yes.
and I measure one, and I know its value.
Mm-hmm.
Does that mean that the other one could potentially still not be measured? But when it is measured, it will have the same value.
Right. When you measure one, it instantly collapses the other, actually.
Okay, that was my question.
Yeah. Good. I mean, I say that's a simplification again of language, but you can think of it that way. Yes. Sorry, you had a question.
So there's no way to tell if something has been collapsed or not then?
Excellent question. If you could tell whether something's been collapsed or not, you could measure one and use that as synchronization, faster than light synchronization, right? Yeah, you can't. The process of telling whether something's in superposition or not would just collapse it.
It seems like you would be able to tell through some of the sort of quantum computation, like you do some computation on it, and then
Yes.
if it was collapsed, it would only be this state, and if it wasn't, it would sometimes be this, sometimes be that.
You would think so, but
think so?
in fact, it is not the case.
I believe you. I was just
Yes.
wondering if you could say. Is there a reason? Is there an intuition why it's not the case? Is there like an obvious,
Is there an
like-
intuitive? Can I say it intuitively?
Shut up and do the math.
Shut up and calculate. That's a good way out. I'm not sure I can say it intuitively. I can say that if you do just pencil and paper it, try it yourself. Try and come up with some sequence of operations you could do on the other qubit, which would reveal it as having been collapsed or not. Then maybe, but yes.
Doesn't this coordination communication conversation that we're having violate causality? Or does it?
Yes, this is the critical thing. It does not violate causality. If we could communicate, then it would violate causality. But since we coordinate, it does not violate
But
causality.
the statement you said was if you measure, the other one is going to be collapsed as well.
Yes.
Right?
Yes.
The act of measurement is in your control, right?
Yes.
So how can that happen on the other side for the other qubit if you don't have communication? Because that's
Well, let's define what communication is. Communication is I have a bit, either 0 or 1, and I'm able to send it to you in some way.
somehow,
Yes.
a state that is not collapsed be communicated to the other side. That at least my intuitive understanding.
Yeah, I mean, this is a language problem. The qubits are communicating, but we can't get information through them, basically. Might be able to say that. Or I use the term coordinating to try and avoid this problem. Other times in the literature, you'll just see the word correlated, which tries to avoid that whole problem.
But coordination, the word here,
Yes.
when you're using it, it has an action that you have performed.
Yes.
On
So
one, right?
you control when you measure a qubit, it collapses the other. But there's no way you can change causality in that other qubit's frame. Basically, there's no way you can get information from your frame into that frame, which would affect their causality. All we can know is we have generated the same random numbers, basically. Yeah.
So it's kind of like pre-coordination. So these are
I want to avoid that. Pre-coordination is the qubits decided ahead of time, which is not the case.
until you measure, or until these.
At the time they measure, they decide whether they're going to 0 or 1, and they somehow communicate that, correlate, whatever, to the other qubit, and it goes in the same. Yes.
So if you cannot communicate, what's the practical application of it?
Great question. We're going to get into quantum teleportation on the very next slide. First, I want to tell a funny story about this. So, you may have heard the phrase "spooky action at a distance." This is Einstein coined that. He was referring to this. So Einstein, Podolsky, and Rosen are 3 physicists who actually came up with the idea of quantum entanglement. They call it the EPR paradox. They're like, the workings of quantum mechanics result in this. This is obviously absurd, therefore quantum mechanics is garbage, was the basic argument. But then the experiments came out and they're like, nope, this is how it works. The universe is in fact absurd, locality is broken, and so it's kind of funny that the EPR paradox is originally designed to discredit quantum mechanics, turned out to be the actual way the universe works. I think it's a great little story. Okay, any other questions about entanglement? Yes.
Yeah. Let's say the same problem, the qubits apart.
Yes.
If we say that this has a certain probability of collapsing to 0 or collapsing to 1, and then we observe that it collapses to 1,
Yes.
how can we justify that our presumption that it had a probability of collapsing to 0 was valid?
Excellent question. Excellent question. The answer is you just do it a whole bunch of times and you see that you get a 50% distribution of values.
Exactly, they won't be occurring at the same time.
Experimentally, we know that they occur at the same time. With the 2013 experiment, it entangled qubits, took them far apart. It used.
Oh, no, I mean,
Okay.
the same pair, the same qubits.
Yes.
It happened at time x.
Yes.
And now you take another pair of qubits, and this is another pair of qubits, but not necessarily the same ones.
Yes.
So until it happened at that time, that space, or whatever, you can't really tell that this was happening in probability.
1/2. You're questioning. Okay, so they could have decided ahead of time, for example, maybe, or.
Yeah, or probably the language of probability itself is not applicable.
It works. Probability works. I mean, it's just the amplitude squared gives you the classical probability of it collapsing to 0 or 1, I guess. I'm not 100% sure what you're driving at. So
I mean, the question is once observed, then we rationalize.
once observed, then we rationalize. Yes, and then if we do that if we do the experiment a whole bunch of times, we see that it's about a 50% chance of them both being 0 or both being 1. Which, in fact, I will show that to you live on a quantum computer that we do that. Okay. All right, let's move on. Teleportation. This is the actual use which you asked about. And you've probably read about quantum teleportation again in pop science articles. Needless to say, their explanation was complete trash. It made no sense at all. But now it will make sense to you. Okay? It's the process by which we take an arbitrary qubit state and transfer it across space and time somewhere else. So you use entangled qubits as a sort of bridge to send a qubit from one place to another. And here's a very important thing. It's called the no cloning theorem. You can transfer qubit states, so you can cut and paste them, but you cannot copy them. You cannot copy and paste a qubit state. You cannot clone it. This is called the no cloning theorem. It's actually pretty simple to prove. You just show that any such operation would not be reversible or its own inverse. But we're not going to go do that. And here's an important thing. The teleportation, despite using a faster than light phenomenon of entanglement, is not itself, the whole protocol is not itself faster than light for communication because you actually must exchange 2 classical bits. So if I'm teleporting my qubit to you, in addition to us having an entangled qubit pair, I also have to send you 2 bits of information. And we'll show why that is in the next slide. Does everyone kind of conceptually grasp the, I guess, the purpose of quantum teleportation? Okay. So here's what the circuit looks like. We're not going to go over the math. There are appendices to this slide deck, which you can see after the class to go over the math, but it gets a bit complicated, so we're not going to do it. So we have the qubit that we want to teleport here. We call it T, and its value is phi. It's just this generic qubit value. It can be any value. And then we have these 2 qubits, A and B, which are both initialized to 0. Now you'll recall this is the entanglement circuit. So these 2 qubits are entangled, all right? Now after they're entangled, we'll say we have Alice and Bob. Alice wants to send her entangled qubit to Bob. So Alice has these 2 qubits. Bob has this qubit. And these 2 qubits are entangled. So the qubits are these 2 qubits are separated right after being entangled, basically. Now Alice then entangles her qubit she wants to teleport with the other 2 qubits. So it's a 3-qubit entangled system. If you were to write out the product state, you wouldn't be able to factor it into 3 qubits. Then she puts this qubit through the Hadamard gate. Finally, Alice measures both qubits in her possession, and those are the 2, and this results in 2 classical bits. These are the 2 bits that Alice has to send to Bob. And the measurement result of this bit determines whether Bob has to put run his qubit through an or a bit flip gate, and the measurement result of this qubit controls whether Bob has to run his qubit through a new type of gate, which we haven't seen before. It's called the phase flip gate, or Z, and this is what the matrix looks like. And basically, once Bob has applied those 2 gates, or neither gate, if both of these end up being 0, Bob doesn't have to apply anything. He'll end up, somewhat magically, with Alice's qubit value she wants to teleport. Pretty nifty, huh? Pretty nifty. And you might be like, well, we're already exchanging a qubit here. Why do we even care? Like, we're obviously just giving a qubit to Bob. Like, couldn't Alice just give her a qubit, like, right there? So what you can do is you can pre-entangle like a whole bunch of qubits, like a few billion qubits or something. And then you ship them by mail. They're called EPR halves. You ship them by mail or something. So Alice and Bob have like a big repository of these entangled qubits. And then anytime Alice wants to send a qubit to Bob, she can just use up one of the EPR pairs. EPR halves. EPR pairs. And at that point, that EPR pair has been collapsed, can no longer be used. So it's a non-renewable resource. But Alice can just send as many qubits as she wants over to Bob. Okay? Now, you might be saying, well, I don't really get this. The math is in the appendix if you really want to go see it. It gets pretty complicated. But I think I did an okay job of explaining it. So, okay. You might be like, okay. Oh, by the way, I forgot to say, really cute, really important thing. You may have heard that we can simulate quantum computers on a classical computer, but it takes exponential slowdown or exponential memory. This is the reason. If 2 qubits become entangled, you have to keep their full product state around. So if like n qubits become entangled, you have a vector of size 2 to the n you have to keep in memory. And that is why it takes exponential memory to simulate a quantum computer on a classical computer. Pretty nifty. OK. So you may be like, OK, this is all pretty interesting. Further learning goals. You can learn the Deutsch-Jozsa algorithm. That's the one with n bits that I talked about. And also Simon's periodicity problem, which is another figure out some property about this function. I'm not going to talk about the complexity stuff. But anyway, you can also learn Shor's algorithm, Grover's algorithm, quantum cryptographic key exchange. That one's actually pretty simple. I recommend looking at that. You can learn how they're actually implemented in physical terms if you care about that. An important thing, quantum error correction. Since these systems are so small, like a spare cosmic ray could just come out of nowhere and just wreck your entire computation, you need very, very stringent error correction schemes. So I think theoretically, it takes 5 physical qubits for a single logical qubit like we've been operating at. In practice, it's looking more like we'll need 1 or 200 to get like a qubit of like 100% probability like we've been using, pretty much. So that's something to keep in mind. Like when we see like Google's coming out with a 30 qubit computer, that maybe doesn't mean as much as we'd hope. It may only get us like 2 or 3 really high quality qubits. And also quantum programming language design, which I will go over because I'll show you a Q-sharp example. But anyway, recommended textbooks. This one is my absolute favorite, has the same title as the name of the talk, Quantum Computing for Computer Scientists. This algorithm is by our friend David Mermin, the Shut Up and Calculate guy. It is a meat grinder of a textbook, but I started out with this one. It was horrifying. It was just like, but it skips a lot of steps, basically. It's more symbolic manipulation. You won't see as many vectors and matrices. I like to write out the vectors and matrices to see what's going on, which gets really unwieldy when you're writing out like a 64 by 64 vector or matrix. But I like to have both of these, you know? So I'll use this to fill in the gaps with this. This has more interesting asides, stuff like that. This is also in the MS library. There's another one called Quantum Computing and Gentle Interaction, also in the MS library. I've heard mixed reviews or semi-decent reviews of it. I haven't looked at it myself. There's also the Microsoft Quantum Development Kit. They have the docs. They're actually pretty nice. They include a quantum computer simulator and Q-sharp, as we'll see. Now, I said I would end the talk on some skepticism, which there's an article came out, I think it was Quantum Magazine, pretty prominent recently, interview with a mathematician who believes that physically realizable quantum computers cannot exist. His basic argument, simplifying, is that the amount of noise in the system grows exponentially with the number of qubits. So we cannot get a really large qubit system because our computation will just keep collapsing in the middle of it. And like, it's just like it's an exponential term. And so I would be very sad if this happened. I'd feel like the universe is against me. It'd be very sad if we could not realize the benefits of quantum computing. Like cosmically sad. But anyway, you know, can't argue with the universe. And yeah, you can read that article for some skepticism. I think his name is Gil Kalai, is the mathematician. There's some appendices, but I'm going to do some demos now. OK, the first demo is just the Deutsch oracle problem in Q-sharp. So Q-sharp is based on F-sharp. And we have this function I've written, is black box constant. You take in a black box, and I tell you whether it's constant. Oh, gosh, sorry. Here, of course. OK. We have our function is black box constant, where it takes in a black box, and it just returns a bool. Is it constant or not? And it just uses the same protocol we went over. It allocates 2 qubits, calls 1 input, 1 output, clears them, sets them both to 0, does the preprocessing, flips them, puts them through the Hadamard gate. Then it sends them into the black box. Afterward, it again puts them through the Hadamard gate, and then it measures both of them. And again, if the input result is 1, then it's constant, otherwise it's variable. OK? We have our black boxes defined here. So constant 0, again, remember it's nothing. For constant 1, we flip the output bit. For identity, we run a C0 gate with input as control, output as target. And negation, we use C0 and X, okay? And we just have these, like is 0 constant 0, I call is black box constant with constant 0. And then we have our classical driver. Any quantum computation will have a sort of classical computer to tell it what to do. And so I ask for each of those 4. Well, what's going on? And we can run it, and it runs on a simulator. And we see the output. Is constant 0 constant? True. Constant 1 constant? True. Identity constant? False. Negation constant? False. So there you go. Yeah, we wrote the Deutsch oracle, ran it on a real quantum simulator. We saw that it worked out. OK, the final demo of the day, and then I'll let you get out of here, is, here we go. This is called the IBM Quantum Experience. There is a real world quantum computer that IBM has built. It only has 5 qubits. But they just let you online just drag gates onto this quantum circuit diagram and run it on a real quantum computer. So I thought it'd be pretty nifty if we demonstrated entanglement, right? Live for you on stage. Let's see. So if you remember, the first thing we do is you drag a Hadamard gate onto 1 bit. And then we use the control knot. Oh, no. Can't. OK. So the way the quantum computers are constructed, you can only usually put C0s between certain bits, basically. It's just kind of, otherwise, it's just mechanically impossible. Let's see, can we do that? Nope. OK. How about, success. OK, we did it. Here's our, this is the C0 gate. You can see varying representations of it. It's like the O+. And I say we'll run it on a quantum computer. Oh, right, measurement gates. I forgot. We need to add the 2 measurement gates, obviously. So we're measuring both of these qubits after entangling them. And what we expect is to see them predominantly being 0, 0, and 1, 1, right? Well, let's test it. We'll call it that. And because we can say the result from cache, but I want to do it live for you guys. So I'm going to run a new execution. And you can imagine right now, deep in an IBM research lab, nestled within a dilution refrigerator operating at slightly above absolute 0, we have real qubits being entangled and measured thousands of times for our entertainment. That's pretty cool. That's pretty cool. OK, let's see if it's, oh, here we go. We got the results. And executions, is it, it's pending. OK. So it might take a couple minutes. We can just hang out. Does anyone have any questions while we're waiting for this? Yes?
I have another question. You said this experiment where they sent an entangled qubit up to space in a satellite.
Yes.
Are we good at storing qubits for a long time? I'm really surprised they were able to do that. I thought they kind of...
Yeah. So that was actually a lie. They managed to send the entangled qubit up via laser. But
oh, I see.
yes.
Oh, okay.
I don't think we're that good at storing qubits for a while. I think they're fairly short-lived.
That's what I thought, but
yeah.
I thought maybe there was something.
But yes, they actually, the Chinese satellite experiment, they teleported a qubit up there.
Oh, okay.
So they sent one EPR half up by a laser, and then they used that EPR half to teleport the qubit up there. Pretty cool.
That's awesome.
Yeah.
So we can send entangled qubits by laser.
You can send entangled qubits by laser, yes.
Okay, that's even cooler.
Yeah. Let's see. It's still not. OK, that's fine. Anyway, yes?
You mentioned that there was this new article by the mathematician that said the noise is going to grow faster.
Yes.
I thought the whole purpose of the topological quantum computer was to resist that.
Of course. Any quantum computer will have issues with noise. The topological quantum computer is supposed to be better than its IBM counterparts in terms of noise, but it'll still grow exponentially. Like, it can still be better, but it still runs into the exponential barrier. And so the next couple of years are really sort of make or break for quantum computing, because we now have the ability to create computers which run into this exponential term if it exists. If it exists. And so we will see within the next couple of years whether quantum computing is really possible or not. It's nervous. It makes me nervous. But Yeah, because we'll run into this limit probably like this year. If Google does not manage to demonstrate quantum supremacy, it'll be a bit scary, I guess. But yeah, let's see. We don't have. Maybe I'll just refresh the entire page.
Question.
Yes.
Do we know what Google uses quantum computing for? Like what?
What they use it
application
for?
area? Or
I don't believe we do. I think they just have.
is it experimental mostly?
It is. No. They haven't announced what they use it for. My manager is actually playing around with the D-Wave simulator to.
The Canadian. Is it the Canadian company?
D-Wave is a Canadian company. Yeah, everyone thought they were like really scammy and not really quantum. Now everyone kind of believes that they're quantum, but it's a different paradigm. It's like optimization basically, but it uses quantum computing. They have a simulator you can use. My manager's been using it to kind of play around with finding routes in a network. It has like general applications like that. Wow, this is taking a while.
Your slide deck is publicly available somewhere?
Yeah, it's in the invitation, and I think it'll probably be posted on the ResNet website, or I'll post it online.
So that application is like a graph search type of application?
Yeah, it's optimized. You're able to express the network graph in terms that like an optimization result would be the least energy path in terms of like the least cost path through the graph, sort of. That's different than the way than the paradigm.
Like open shortest path.
Come on, why isn't it going? It's pending. I'll be really sad if this doesn't finish in time. Oh well.
So on D-Wave, I saw a presentation, someone was saying that you could do classically faster than what they were able to do on D-Wave. So they've improved it now, or what's
I don't know,
changed?
actually. I haven't looked into that. It's probably, they're probably about comparable, I would say. Because given that it's just like optimization, and especially with the explosion of machine learning, there's been a lot of development in making optimization better.
Right.
Optimization is like you have a surface, and you're trying to find like the highest point or the lowest point. So there's been a lot of research that goes into that. Well, how about we'll just run it from cache. And, okay. Here we go. Okay, so here's the results from cache. Unfortunately, our real execution didn't finish yet, but so we see that indeed they entangled some different qubits than ours, but we end up with 0, 0 and 1, 1 almost exclusively, but then there's some in the middle because of the error rate, right? So this is on a real quantum computer. We have some error rate where it doesn't exactly work according to our model all the time, but pretty cool. These are entangled and they're measured, and we have that. That's the experimental data right there, that entanglement is a real thing. Yeah. Okay, that concludes the presentation. Thank you very much. I hope you all feel as though you followed the whole thing, no real confusion, and feel that you could keep on learning. This isn't like mad genius science. This is very accessible science. So yeah, thank you very much.